Tonight, we're going to explore something that breaks the most basic rule you think you know about physics. Every force you've ever heard of does the same thing. It pushes or pulls. Gravity pulls you toward the Earth. Electromagnetism pushes magnets apart or snaps them together. The strong nuclear force grips quarks so tightly they can never escape. Push, pull. Push, pull. That's what forces do. But there is a fourth force in nature, and it does something completely different. It doesn't move particles around. It reaches inside a particle and changes what that particle is. A neutron becomes a proton. A quark switches its identity. One type of matter transforms into another type of matter right before your eyes. Without this force, the sun would not shine, atoms would never decay, and the universe would be a frozen, changeless, dead place. This is the weak interaction, and it changes everything. Before we dive in, if you find this kind of deep exploration fascinating, a quick like or subscribe genuinely helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let's start with something you already know, even if you've never really thought about it this way. Forces, in the way physics uses the word, are the things that make particles do something. You're familiar with this from everyday life, even if you don't think of it in terms of particles. Gravity pulls you toward the ground. You feel it right now, pressing you into your chair, keeping your feet on the floor, pulling every raindrop from the sky. Gravity is a force, and what it does is straightforward. It moves things. It pulls massive objects toward each other. Electromagnetism is another force. It holds electrons in orbit around atomic nuclei. It makes magnets snap together or push apart. It carries light from the sun to your eyes. When you touch a table and your hand doesn't pass through it, that's electromagnetism. The electrons in your skin repelling the electrons in the table's surface. Like gravity, it moves things around. It pushes charged particles one way or pulls them another. The strong nuclear force is the third. You may have heard of it, even if the details are fuzzy. This is the force that holds the nucleus of every atom together. Protons are positively charged, and positive charges repel each other through electromagnetism. So protons packed side by side in a nucleus should fly apart. They don't, because the strong force is far more powerful than electromagnetism at these tiny distances. It grips quarks inside protons and neutrons so tightly that under ordinary conditions, nothing can tear them apart. It binds protons and neutrons together so firmly that nuclei can remain stable for billions of years. The strong force is, well, strong. But like gravity and electromagnetism, what it does is fundamentally about pushing and pulling. It moves particles around. It holds things in place or forces things apart. All three of these forces share something in common that's so basic you might not even notice it. They change where particles are. They change how fast particles are moving. They change what direction particles are heading. But they never, under any circumstances, change what a particle is. Gravity can pull an electron toward a massive star, but when that electron arrives, it's still an electron. Electromagnetism can accelerate a proton to nearly the speed of light, but that proton is still a proton. The strong force can bind quarks so tightly they form composite particles, but an up quark inside that composite is still an up quark. These forces move particles around like pieces on a game board, but they never turn a pawn into a rook. They never change the identity of the piece itself. And then there's the fourth force, the weak interaction. And it does something none of the others can do. It reaches inside a particle and changes what that particle is. It turns one type of particle into a completely different type of particle. Not by breaking it apart, not by smashing it to pieces, but by transforming it. One particle goes in, a different particle comes out. The weak force doesn't just move pieces around the board, it changes the pieces themselves. This is what makes the weak interaction unique in all of physics. It is the force of transformation, the force of identity change, the force that makes one kind of matter become a different kind of matter. And to understand what that truly means, you first need to understand what particle identity actually is. When physicists talk about different types of particles, they don't just mean particles moving at different speeds or sitting in different places. They mean fundamentally different things. An up quark and a down quark aren't the same particle behaving differently. They are different particles with different properties. An up quark has an electric charge of plus 2/3. A down quark has an electric charge of minus 1/3. These aren't minor differences. They're as fundamental as the difference between a cat and a dog. You can't make an up quark by spinning a down quark faster, or cooling it down or stretching it out. They're different entities entirely. This concept of particle type is called flavor in physics. It's a slightly whimsical name, but it captures the idea perfectly. Just as chocolate and vanilla are different flavors of ice cream, up and down are different flavors of quark. And flavor is what defines a particle's identity. There are 6 flavors of quark in total: up, down, charm, strange, top, and bottom. Each one is a distinct particle with distinct properties. A charm quark is not a heavier version of an up quark. It's a different thing altogether, with its own mass, its own interactions, its own role in the universe. There are also particles called leptons, and they come in flavors too. The electron is one flavor, the muon is another, the tau is a third. Each has an associated neutrino. The electron neutrino, the muon neutrino, and the tau neutrino. Again, these aren't the same particle in different states. They're different particles entirely. Now, here's why all of this matters. Most forces are completely blind to flavor. Gravity pulls on anything with mass, regardless of whether it's an up quark or a down quark, an electron or a muon. Electromagnetism acts on anything with electric charge, regardless of flavor. The strong force acts on anything with color charge, the quantum property that quarks carry, regardless of whether the quark is up or down or strange or charm. These forces don't care about flavor. They treat different flavors the same way, as long as the relevant charge is present. The weak interaction is different. The weak interaction is the only force in nature that can change a particle's flavor. It can reach inside a neutron, find a down quark, and turn it into an up quark. It can take an electron and turn it into an electron neutrino, or vice versa. No other force in the universe has this power. Think about it this way. Imagine you have a box of colored balls: red, blue, green, yellow. Gravity can move the balls around inside the box. Electromagnetism can push them together or pull them apart. The strong force can clump them into tight clusters. But none of these forces can change a red ball into a blue ball. Only the weak force can do that. It reaches into the box, picks up a red ball, and when you look again, the ball is blue. It didn't break apart. It didn't get replaced by a different ball. It transformed. That is what the weak force does to particles. This might sound abstract, but the consequences are enormous. Because if particles could never change their identity, The universe as you know it could not exist. The first real evidence that nature had this power came from a phenomenon called radioactive decay, specifically a type called beta decay. And the story of how scientists uncovered what was really happening during beta decay is one of the most fascinating detective stories in the history of physics. In the late 1800s, physicists discovered that certain atoms are unstable. They spontaneously emit particles and energy, transforming into different atoms over time. Henry Becquerel discovered this phenomenon in 1896, when he found that uranium salts could expose photographic plates even in complete darkness. Something was coming out of those atoms, some kind of invisible radiation that could pass through solid materials and darken photographic film. Marie Curie and her husband Pierre studied this phenomenon extensively, discovering new radioactive elements. Ernest Rutherford classified the radiation into 3 types. Alpha radiation could be blocked by a sheet of paper. Beta radiation penetrated paper but was stopped by thin metal. Gamma radiation could pass through almost anything. The beta rays turned out to be electrons, high-speed electrons shooting out of atomic nuclei, and this was immediately strange. Electrons aren't supposed to be inside the nucleus. The nucleus contains protons and neutrons. Electrons orbit the nucleus at a distance. So where were these electrons coming from? The answer, it turned out, was that the electrons were being created in the moment of decay itself. They didn't exist inside the nucleus before the decay happened. They were born during the transformation. Something inside the nucleus was changing, and an electron was being produced as a result. But here's where the real mystery began. When physicists carefully measured the energy of the electrons emitted during beta decay, they found something deeply troubling. The electrons didn't all come out with the same energy. In other types of radioactive decay, like alpha decay, the emitted particles always carry a specific, predictable amount of energy. If a particular isotope emits an alpha particle, that particle always has the same energy, every single time, for every atom of that type. This makes perfect sense. The atom starts with a certain amount of energy. It ends with a certain amount of energy. The difference is carried away by the alpha particle. Energy is conserved. The books balance perfectly. But beta decay was different. The electrons came out with a continuous range of energies. Sometimes the electron carried nearly all the expected energy. Sometimes it carried barely any. And the total energy of the electron was almost always less than the expected amount. Energy seemed to be vanishing into thin air. Some very prominent physicists seriously considered exactly that. Niels Bohr, one of the founders of quantum mechanics, suggested that maybe energy conservation simply doesn't hold during certain nuclear processes. Maybe at the subatomic level, energy can appear and disappear. This was a radical proposal, and it shows just how desperate the situation had become. Bohr wasn't a fringe thinker making wild claims. He was one of the most respected physicists alive, and he was willing to abandon energy conservation to explain what beta decay was doing. But in 1930, another physicist proposed a different solution. Wolfgang Pauli wrote a letter to a group of colleagues meeting in Tübingen, Germany. He couldn't attend the meeting himself because, as he explained in the letter, he was indispensable at a dance in Zurich. But the letter he sent would change physics forever. Pauli proposed that during beta decay, the nucleus emits not one particle, but 2. The electron that everyone could see and measure, and a second particle that nobody had ever detected. This second particle, Pauli suggested, was electrically neutral, meaning it wouldn't interact with electromagnetic detectors. It had extremely little mass, perhaps no mass at all, and it was carrying away the missing energy. Pauli initially called this hypothetical particle the neutron, but 2 years later, James Chadwick discovered the actual neutron, the heavy neutral particle inside atomic nuclei, and claimed the name. So the Italian physicist Enrico Fermi gave Pauli's particle a new name, the neutrino, which in Italian essentially means the little neutral one. Pauli himself was not entirely comfortable with his own idea. He reportedly said that he had done a terrible thing. He had proposed a particle that could not be detected. In physics, proposing something fundamentally undetectable is dangerous territory. If a particle can't be observed or measured, how do you know it exists? How do you distinguish a real but undetectable particle from no particle at all? But the neutrino hypothesis had one enormous advantage. It saved energy conservation. If you included the neutrino's energy in the accounting, the books balanced perfectly. Every beta decay event produced an electron and a neutrino, and the combined energy of both particles always added up to the expected total. Sometimes the electron carried most of the energy and the neutrino carried very little. Sometimes the neutrino carried most of the energy and the electron carried barely any. But the sum was always the same, every time, for every decay. Energy was conserved after all. The neutrino also solved another problem that had been troubling physicists. During beta decay, angular momentum, the rotational equivalent of linear momentum, also seemed to not be conserved. The neutrino fixed this too. Its intrinsic spin accounted for the missing angular momentum. A single invisible particle resolved two fundamental crises simultaneously. But for 26 years, the neutrino remained a theoretical ghost. Everyone believed it probably existed because the mathematics worked so beautifully with it. But nobody had actually detected one. Neutrinos interact so feebly with ordinary matter that they pass through almost everything. Trillions of neutrinos from the Sun pass through your body every single second, and essentially none of them interact with any atom inside you. They fly through the entire Earth as if it simply weren't there. Detecting such a particle seemed almost impossible. Then, in 1956, two American physicists, Frederick Reinese and Clyde Cowan, managed to do it. They set up a detector near a nuclear reactor at the Savannah River plant in South Carolina. Nuclear reactors produce enormous numbers of antineutrinos as a byproduct of the fission process. Reinese and Cowan built a tank filled with water laced with cadmium chloride. When an antineutrino from the reactor struck a proton in the water, it would produce a positron and a neutron. The positron would immediately annihilate with a nearby electron, producing a distinctive pair of gamma rays. The neutron would be captured by a cadmium nucleus a few microseconds later, producing another burst of gamma rays. This double flash, two signals separated by a precise time gap, was the unmistakable signature of a neutrino interaction. They found it. After months of painstaking data collection, carefully filtering out background noise and false signals, Reinese and Cowan confirmed that antineutrinos from the reactor were interacting with protons in their detector, exactly as Pauli had predicted 26 years earlier. They sent a telegram to Pauli. "Dear Professor Pauli, we are happy to inform you that we have definitely detected neutrinos." Pauli reportedly celebrated with a case of champagne. The ghost particle was real. But confirming the neutrino's existence was only the beginning of understanding what was actually happening during beta decay. Because the deeper question remained. What force was responsible for this transformation? What mechanism could reach inside a neutron and change it, producing an electron and an antineutrino in the process? To answer that, we need to look inside the neutron itself, and what we find there is remarkable. A neutron is not a fundamental particle. It's a composite made of three quarks held together by the strong force. Specifically, a neutron contains one up quark and two down quarks. A proton, by contrast, contains two up quarks and one down quark. The difference between a neutron and a proton comes down to the flavor of a single quark. Change one down quark into an up quark, and you've turned a neutron into a proton. And that is exactly what happens during beta decay. Inside the neutron, one of the down quarks transforms into an up quark, not by breaking apart, not by being destroyed and replaced. The down quark itself changes identity. It was a down quark with a charge of -1/3 and a particular mass. Then, through the weak interaction, it becomes an up quark with a charge of +2/3 and a different mass. The particle that existed a moment ago is gone. A fundamentally different particle has taken its place. During this transformation, the quark emits a W- boson. This boson carries away the difference in electric charge. The down quark had a charge of -1/3. The up quark has a charge of +2/3. The total change is +1 unit, which means the W boson must carry away -1 unit of charge. And it does. Charge is conserved. Nothing is created from nothing. The books balance precisely. But the W- boson is extraordinarily massive, roughly 86 times the mass of a proton. It's so heavy that it cannot exist for more than an unimaginably brief instant. The uncertainty principle in quantum mechanics permits this. For an incredibly short time, energy can be borrowed from the vacuum to create a particle far heavier than the available energy would normally allow, as long as that particle vanishes almost immediately. The W boson exists for roughly 10 to the -25 seconds. That is so brief that light itself, traveling at 300,000 kilometers per second, would cover only a tiny fraction of the width of a proton in that time. During its vanishingly brief existence, the W- boson decays. It transforms into an electron and an electron anti-neutrino. These two particles fly away from the nucleus, carrying energy and momentum with them. The electron is what the early physicists detected as beta radiation. The antineutrino is the ghost particle Pauli predicted, the one that carries away the energy that had seemed to be missing. So the full picture of beta decay, at the deepest level we currently understand, is this. A down quark inside a neutron emits a W- boson and becomes an up quark. The neutron has now become a proton because it contains 2 up quarks and 1 down quark, instead of 1 up and 2 down. The W- boson, existing for only the briefest possible instant, decays into an electron and an electron antineutrino. The electron shoots out of the nucleus at high speed. The antineutrino flies away, barely interacting with anything it encounters. The atom has changed from one element to another. A particle has changed its fundamental identity. And it was the weak interaction, and only the weak interaction, that made it happen. This is worth pausing on, because what just happened is genuinely strange. A particle that existed, a down quark, is no longer a down quark. It is now an up quark. It didn't split into smaller pieces. It didn't get rearranged. The down quark itself became something else entirely. Something with a different charge, a different mass, a different identity. No other force in nature can do this. No other force can change the flavor of a particle. Gravity acts on mass and energy, but a quark that falls through a gravitational field remains the same flavor of quark when it arrives as when it started. Electromagnetism acts on electric charge, but a down quark that interacts electromagnetically remains a down quark. The strong force binds quarks together with incredible power, but an up quark bound inside a proton by the strong force is still an up quark. It doesn't become a strange quark or a charm quark because the strong force acted on it. The strong force is completely blind to flavor. It treats all quark flavors identically. Only the weak interaction has the power to change one flavor into another. Only the weak force can turn a down quark into an up quark, or a strange quark into an up quark, or an electron into an electron neutrino. This is its unique role in the universe. While the other forces push and pull and bind and repel, the weak force transforms. It is the force of change itself. And the consequences of this power ripple across the entire universe. Because if particles could never change their identity, if the flavor a particle was born with was the flavor it kept forever, then a neutron would remain a neutron for all eternity. It would never become a proton. It would never emit an electron. There would be no beta decay. Without beta decay, the universe would be a radically different place. The elements you're made of, the carbon in your cells, the oxygen you breathe, the calcium in your bones, many of these were forged in processes that depend on the weak force's ability to transform one particle into another. The slow, steady burning of the sun depends on it. The explosive deaths of massive stars depend on it. The delicate balance of hydrogen and helium in the early universe depends on it. Without the weak force, matter would be static. Particles would be born with a fixed identity and keep that identity forever. There would be no mechanism for one type of atom to become a different type of atom through decay. No mechanism for stars to convert hydrogen into helium in the way they actually do. No mechanism for the radioactive processes that heat the interior of the Earth and drive plate tectonics and power our magnetic field. The universe would be locked into its initial state, unchanging, unyielding, and lifeless. But the universe is not frozen. Matter is not static. Particles do change their identities. Neutrons do decay into protons. Quarks do switch their flavors. Atoms do transform from one element into another. And every single one of these transformations, every identity change that any particle anywhere in the universe has ever undergone, happened because of the weak interaction. Every atom of carbon-14 that decays in an archaeological sample, allowing scientists to determine the age of ancient artifacts, decays because the weak force transformed a down quark into an up quark inside one of its neutrons. Every atom of potassium-40 that decays deep inside the Earth, generating the heat that keeps our planet's interior molten and its magnetic field active, decays because the weak force changed a particle's flavor. The weak interaction is not some obscure footnote in the physics textbook. It is not some minor force that barely matters compared to the others. It is the force that makes matter transformable. It is the mechanism through which the universe changes, evolves, and creates new forms of matter from old ones. Every other force moves particles from place to place. The weak force moves particles from one identity to another. And through all of these transformations, the weak force follows strict rules. These identity changes are not random or chaotic. Every time a particle changes its flavor through the weak interaction, specific quantities must be conserved. Energy is conserved. The total energy before the transformation equals the total energy afterward. Momentum is conserved. Electric charge is conserved. When a down quark becomes an up quark, the charge changes from -1/3 to +2/3, a total shift of +1. So the W boson that carries away the difference has a charge of exactly -1, balancing the equation perfectly. When that W boson then decays into an electron and an antineutrino, the electron carries a charge of -1, matching the W boson's charge. A quantity called lepton number is also conserved. Before the decay, there are no leptons present, so lepton number is 0. After the decay, the electron contributes +1 and the antineutrino contributes -1, giving a total lepton number that is still 0. Everything adds up. Everything balances. So when the weak force transforms a particle, it isn't violating the laws of physics. It is the laws of physics. The transformation is permitted precisely because the conservation laws allow it. The universe doesn't change arbitrarily or randomly. It changes according to precise quantum rules. And the weak interaction is the mechanism through which those rules permit one of the most extraordinary phenomena in all of nature: the transformation of one particle into another. So now you understand what the weak interaction does. It changes the identity of particles. it transforms one flavor into another. But understanding what a force does is only half the story. The other half is understanding how it does it. What is the actual machinery of this transformation? When a down quark becomes an up quark inside a neutron, what physically happens? What carries the transformation from one state to the other? How does nature accomplish this extraordinary trick of turning one type of particle into a completely different type of particle? To answer this, we need to understand something fundamental about how forces work at the quantum level. Because in quantum physics, forces don't work the way you might imagine. You might picture a force as some kind of invisible field pushing or pulling on a particle, like wind pushing on a sail. That's a reasonable classical picture. But at the quantum level, the picture is different. Forces are carried by particles. This is one of the most important ideas in modern physics. Every fundamental force has associated particles called force carriers, or more formally, gauge bosons. When two particles interact through a force, they do so by exchanging these carrier particles between them. The electromagnetic force is carried by photons. When two electrons repel each other, what's actually happening at the quantum level is that they're exchanging photons back and forth. The strong nuclear force is carried by gluons. When quarks bind together inside a proton, they're constantly exchanging gluons, passing them back and forth billions of times every fraction of a second. The weak interaction has its own force carriers. There are three of them: the W+ boson, the W- boson, and the Z boson. And these three particles are the physical agents of transformation. They are the machinery through which the weak force changes one particle into another. The W bosons are the ones that do the heavy lifting when it comes to identity change. Let's look at how this works in detail, because the mechanism is elegant and precise. When a down quark transforms into an up quark during beta decay, it doesn't just spontaneously switch from one thing to another in some vague, undefined way. What happens is that the down quark emits a W- boson. In that instant of emission, the down quark becomes an up quark. The W boson carries away the difference. It carries away the change in electric charge, the change in other quantum numbers. Essentially, it carries the identity difference between what the particle was and what the particle has become. The W boson is charged. The W+ boson carries a positive electric charge of +1. The W- boson carries a negative electric charge of -1. This is critical, because electric charge must always be conserved. When a down quark with a charge of -1/3 transforms into an up quark with a charge of +2/3, the total change in charge is +1. That means a particle with a charge of -1 must be created to balance the books. And that particle is the W- boson. It carries away exactly the right amount of charge to make everything add up. Once the W- boson is emitted, it doesn't stick around. It can't. It's far too heavy to exist for more than the briefest possible instant. Within roughly 10 to the -25 seconds, the W boson itself decays. It transforms into other particles, typically a lepton and its associated antineutrino. In the case of ordinary beta decay, the W- boson decays into an electron and an electron antineutrino. These two particles then fly away from the interaction point, carrying energy and momentum into the wider world. But beta decay is just one example. The W bosons can facilitate many different flavor changes. A W+ boson can turn an up quark into a down quark, which is the reverse of what happens in ordinary beta decay. This reverse process actually occurs inside the Sun, as we'll explore later. A W boson can turn a charm quark into a strange quark, or a strange quark into an up quark. It can turn a muon into a muon neutrino. it can turn a tau into a tau neutrino. Any flavor change among quarks or leptons is mediated by a W boson. Think of the W boson as a courier that carries identity change between particles. It arrives at a quark, picks up the quark's current identity, and delivers a new one. It takes the difference in quantum numbers, the change in charge, the shift in flavor, and carries all of that away as a physical particle. Then it delivers that package to the leptons it decays into. Nothing is lost. Nothing appears from nowhere. The identity change is physical, carried by a real particle, governed by precise mathematical rules. The Z boson plays a different role. Unlike the W bosons, the Z boson is electrically neutral. It carries no charge. And because it carries no charge, it cannot change the flavor of a particle. When a Z boson is exchanged between two particles, the particles remain what they are. A down quark that interacts through a Z boson is still a down quark afterward. A neutrino that exchanges a Z boson with another particle is still the same type of neutrino. So what does the Z boson actually do? It mediates what physicists call neutral current interactions. These are weak force interactions where particles scatter off each other, exchanging energy and momentum without changing identity. A neutrino, for instance, can bounce off an electron by exchanging a Z boson. Both particles remain the same flavor afterward, but they've exchanged a kick of energy and momentum. The neutrino changes direction, the electron recoils, and a Z boson carried the interaction between them. This matters because it shows the weak force isn't exclusively about transformation. It can also cause particles to interact without changing what they are. But the Z boson's interactions are still distinctly weak force interactions. They follow the same mathematical structure and occur at the same short range as W boson interactions. The Z boson is part of the same family. It simply represents the neutral face of the weak interaction, the version that preserves identity rather than changing it. Now, there's a question that probably occurred to you several minutes ago. If the weak interaction is a fundamental force like electromagnetism and the strong force, why is it called weak? The name makes it sound feeble, unimportant, a minor player in the physics of the universe. But that name is misleading. The weak interaction is not actually weak in the way you might think. Its intrinsic strength, the fundamental coupling constant that describes how powerfully it acts when it does act, is actually comparable to electromagnetism.
The reason it appears weak has nothing to do with its intrinsic power and everything to do with its range. The electromagnetic force has infinite range. A photon, the carrier of the electromagnetic force, is massless. It weighs nothing. Because it's massless, it can travel any distance. It can carry the electromagnetic force across the room, across a continent, across a galaxy, across the observable universe. Two charged particles separated by billions of light years still interact electromagnetically, even though the force is incredibly faint at that distance. The photon's masslessness gives electromagnetism its infinite reach. The weak force carriers are not massless. The W bosons have a mass of about 80.4 giga-electron-volts. The Z boson has a mass of about 91.2 giga-electron-volts. To put that in perspective, a proton has a mass of about 0.938 giga-electron-volts. So the W boson is roughly 86 times heavier than a proton, and the Z boson is roughly 97 times heavier. These are extraordinarily massive particles. They are among the heaviest fundamental particles we have ever discovered, and this mass has a devastating consequence for the weak force's range. To understand why, you need to appreciate a deep connection between quantum mechanics and force range. In quantum field theory, when two particles interact, they exchange a virtual force carrier. This virtual particle doesn't need to obey the normal relationship between energy and mass.
It can borrow energy from the vacuum, as long as it pays that energy back quickly enough. This is permitted by the Heisenberg uncertainty principle, which says that the uncertainty in energy, multiplied by the uncertainty in time, must be at least a certain minimum value related to Planck's constant. The more energy you borrow, the faster you have to pay it back. A massless photon can borrow essentially zero energy and exist for an arbitrarily long time, traveling an arbitrarily long distance. That's why electromagnetism has infinite range. But a W or Z boson has enormous mass. Creating one, even as a virtual particle, requires borrowing an enormous amount of energy. And that enormous energy debt must be repaid almost instantly. The W boson can only exist for about 10 to the minus 25 seconds before the uncertainty principle demands its energy back. In that unimaginably brief time, even traveling at close to the speed of light, the W boson can cover a distance of only about 10 to the minus 18 meters. That is roughly 1,000th the diameter of a proton. 1,000th the size of something that is already 100,000 times smaller than an atom. This is the range of the weak force. It acts only over distances smaller than about 10 to the minus 18 meters. Anything farther apart than that, and the weak force simply cannot reach. The W and Z bosons are too heavy to travel any farther before they must vanish. They're born and they die in the same breath, in the same unimaginably tiny volume of space. This is why the weak interaction appears weak, not because its fundamental strength is low, but because it can only act across incredibly tiny distances. In any process that involves particles more than about 10 to the minus 18 meters apart, the weak force is essentially zero. It doesn't contribute, it doesn't participate. Only when particles are packed incredibly close together, closer than 1,000th of a proton's diameter, can the weak force act. Compare this to electromagnetism, where the photon's masslessness lets the force reach across the entire universe, or to the strong force, which has a range of about 10 to the minus 15 meters, roughly the size of a proton. The strong force's range is limited too, but it's about 1,000 times longer than the weak force's range. The weak force has the shortest range of any known interaction. Now, why are the W and Z bosons so heavy? This is one of the deepest questions in particle physics, and the answer connects to one of the most famous discoveries in modern science. The W and Z bosons get their mass from the Higgs field. The Higgs field is a quantum field that permeates all of space. Unlike most quantum fields, the Higgs field has a non-zero value even in a vacuum, even in completely empty space where nothing else exists. It fills the universe like an invisible ocean, and certain particles, as they move through this field, interact with it in a way that gives them mass. The more strongly a particle interacts with the Higgs field, the heavier it is. The W and Z bosons interact very strongly with the Higgs field. They are deeply coupled to it, and as a result, they acquire enormous masses. This is what makes them heavy, what limits their range, what makes the weak force appear weak, and what confines its transformative power to the tiniest distances imaginable. The photon, by contrast, does not interact with the Higgs field in this way. It passes through the Higgs field without coupling to it, remaining massless and retaining its infinite range. The difference between the photon and the W and Z bosons, between the infinite range of electromagnetism and the minuscule range of the weak force, comes down to how these particles interact with the Higgs field. This is remarkable because it means the apparent weakness of the weak interaction isn't some intrinsic property of the force itself. It's an accident of the Higgs field. If the Higgs field didn't exist, or if its properties were different,
the W and Z bosons would be massless. The weak force would have infinite range, just like electromagnetism. It would be just as visible, just as dominant, just as far-reaching. But the Higgs field does exist. It does give the W and Z bosons their mass, and so the weak force is confined to the smallest distances, hidden away inside atomic nuclei, acting only when particles press up against each other in the most intimate possible way. There is another way in which the weak force is unique among all the fundamental forces, and this one is perhaps the strangest of all. The weak interaction violates parity. It treats left and right differently. It is the only force in nature that does this. To understand what this means, imagine looking at a physical process in a mirror. In a mirror, left and right are reversed. Your right hand appears as a left hand. A clock running clockwise appears to run counterclockwise. If you watch a ball bouncing off a wall in a mirror, the physics looks perfectly normal. Gravity works the same way. Electromagnetism works the same way. The strong force works the same way. If you watched any process governed by these three forces in a mirror, you could not tell you were watching a reflection. The mirror version obeys all the same laws as the original. Left and right are interchangeable as far as these forces are concerned. Physicists call this symmetry-parity conservation. It was long assumed that parity was a fundamental symmetry of nature, that the laws of physics made no distinction between left and right. It seemed obvious. Why would the universe care which direction you called left and which you called right? Those are just labels we invented. Surely nature doesn't prefer one over the other. In 1956, two theoretical physicists, Sung-Dao Lee and Chen-Ning Yang, proposed that maybe the weak interaction doesn't conserve parity after all. They had been studying a puzzle involving the decay of certain particles called kaons, and they realized the puzzle could be resolved if the weak force distinguished between left and right. Their proposal was radical. It went against decades of assumption. Many physicists were skeptical, but in 1957, an experimentalist named Qian-Xiong Wu designed and carried out a beautiful experiment to test the idea.
She took atoms of cobalt-60, a radioactive isotope that undergoes beta decay, and cooled them to temperatures very close to absolute zero. At these extremely low temperatures, she could align the nuclear spins of the cobalt atoms using a magnetic field, essentially making all the nuclei spin in the same direction. If parity were conserved, the electrons emitted during beta decay should come out equally in both directions, along the spin axis and against it. There should be no preference. Left and right should be identical. But that's not what Wu found. The electrons came out preferentially in one direction. There was a clear, unmistakable asymmetry. More electrons were emitted in the direction opposite to the nuclear spin than along it. The weak force was distinguishing between the two directions. It was treating one direction differently from the other. Parity was violated. This result stunned the physics community. Li and Yang received the Nobel Prize in Physics in 1957, the same year the experiment confirmed their prediction. And the result revealed something deeply strange about the weak interaction. The violation goes even deeper than the cobalt-60 experiment showed. Subsequent experiments revealed that the weak interaction only acts on left-handed particles and right-handed antiparticles. To understand what this means, think about a particle moving through space. The particle has a spin, an intrinsic angular momentum. If the particle's spin is aligned in the same direction as its motion, like a bullet spinning clockwise as it moves forward, the particle is called right-handed. If the spin is aligned opposite to the motion, the particle is called left-handed. The weak force only couples to left-handed quarks and left-handed leptons. A right-handed electron does not feel the weak force at all. A right-handed neutrino, if it even exists, would be completely invisible to the weak interaction. This is an astonishing asymmetry built into the fundamental structure of the universe. Every other force treats left-handed and right-handed particles identically. Only the weak force makes a distinction. This is not a minor technical detail. It is one of the most profound facts about our universe. The laws of physics are not symmetric between left and right. If you built a perfect mirror image of our universe, swapping every left for every right and every right for every left, the weak interaction would behave differently. A mirror universe would not obey exactly the same laws as our universe. The weak force breaks a symmetry that every other force preserves. Why? We don't fully know. The mathematical framework of particle physics can describe the violation with extraordinary precision. The theory tells us exactly how the weak force couples to left-handed particles and ignores right-handed ones. But it doesn't tell us why. Why should nature prefer one-handedness over the other? Why should the universe care about the difference between left and right? This remains one of the open questions in fundamental physics. We can describe the asymmetry, we can measure it with incredible accuracy. We can predict its consequences in detail, but we don't understand, at the deepest level, why it exists. Now here's something that ties many of these threads together. The fact that the weak force is carried by massive bosons, the fact that it violates parity, the fact that it has such a short range, these are not independent facts. They are all connected. They are all consequences of a single underlying mathematical structure. In the 1960s and 70s, three physicists, Sheldon Glashow, Abdus Salam, and Steven Weinberg, independently developed a theory that unified the weak interaction with electromagnetism into a single framework called the electroweak theory. This theory showed that the electromagnetic force and the weak force are not truly separate forces. They are two different manifestations of a single underlying electroweak interaction. At very high energies, energies that existed in the first fractions of a second after the Big Bang, the electromagnetic force and the weak force are indistinguishable. There is no difference between them. There are four force carriers, all massless, all with infinite range, all behaving according to a single set of rules. At these extreme energies, the W bosons and the Z boson are massless, just like the photon. They all travel at the speed of light. They all have infinite range. The weak force is not weak. It is identical in strength and range to electromagnetism. But as the universe cooled, the Higgs field settled into its current state, and when it did, it broke the symmetry between the electromagnetic and weak forces. Three of the four force carriers, the W+, the W-, and the Z, acquired enormous masses through their interaction with the Higgs field. The fourth, the photon, remained massless. The single electroweak force split into two apparently different forces. Electromagnetism carried by the massless photon with infinite range, and the weak interaction carried by the massive W and Z bosons with a range smaller than 1/1000th of a proton. This is called electroweak symmetry breaking, and it is one of the most important events in the history of the universe. Before it happened, there was one unified force. After it happened, there were two apparently different forces with vastly different properties. But the underlying unity is still there, encoded in the mathematics, visible in the symmetries of the theory, confirmed by experiments at particle accelerators, where we can recreate, briefly and on a tiny scale, the extreme conditions under which the forces were unified. The electroweak theory was confirmed experimentally in 1983, when physicists at CERN in Geneva discovered the W and Z bosons directly by smashing protons into antiprotons at enormous energies. In the debris, researchers found unmistakable signatures of W and Z bosons being produced and decaying. Their masses matched the electroweak predictions with remarkable precision. Carlo Rubbia and Simon van der Meer received the Nobel Prize in 1984 for this discovery. Further experiments at the LEP Collider, also at CERN, produced millions of Z bosons and studied their properties in exquisite detail. Every measurement confirmed the electroweak theory. The masses, the decay rates, the production probabilities, the angular distributions of decay products. All of it matched theoretical predictions to an extraordinary degree. The electroweak theory is one of the most precisely tested theories in all of science. So the weak interaction is not truly a separate force. It is half of a larger, unified interaction that also includes electromagnetism. The apparent differences between them, the difference in range, the difference in whether parity is conserved, the difference in whether particles change identity, all of these arise because the Higgs field broke the symmetry between them. In the deepest sense, when a down quark transforms into an up quark by emitting a W boson, it is doing something fundamentally related to what happens when an electron emits a photon. The two processes are cousins, born from the same underlying physics, separated by the Higgs field's influence. And this brings us back to the central point. The weak force appears weak because its carriers are heavy. Its carriers are heavy because of the Higgs field, and the Higgs field's role in giving them mass is what hides the true nature of the weak interaction from our everyday experience. At the energy scales we encounter in daily life, the weak force is confined to distances smaller than 1,000th of a proton. It seems feeble. It seems insignificant. But that appearance is a disguise.
Strip away the Higgs field's effect, push the energy up to the levels that existed in the earliest moments of the universe, and the weak force reveals itself for what it truly is. A force as powerful as electromagnetism. A force with infinite range. A fundamental pillar of nature's architecture. But even confined to its tiny range, even hidden away at distances most people will never think about, the weak force does something that no other force in the universe can do. It changes what particles are. It reaches into the heart of matter and rewrites identity. And that power, exercised across distances smaller than 1,000th of a proton, lasting for times shorter than 10 to the minus 25 seconds, shapes the entire cosmos. It powers the stars. It builds the elements. It drives the decay of unstable nuclei. It may even explain why matter exists at all. The machinery of this transformation is precise and beautiful. The W boson acts as the courier of change, carrying charge and quantum numbers from one particle to another, existing for the briefest conceivable instant before decaying into the products of transformation. The Z boson mediates neutral interactions, allowing the weak force to make its presence felt even without changing flavor. The Higgs field gives the carriers their mass, confining the force's reach, but not diminishing its fundamental power. And parity violation reveals that this force operates according to rules unlike any other in nature, distinguishing left from right in a universe where every other interaction treats them as identical. This is the machinery. These are the gears and levers of transformation. And now that you understand how the weak force does what it does, it's time to see what it accomplishes. Because this force, hidden away at the tiniest distances, operating through particles that exist for fractions of an instant,
quietly shapes the entire universe from the cores of stars to the first seconds after the Big Bang. You now understand what the weak force does. It changes the identity of particles. And you understand how it does it, through the exchange of massive W and Z bosons that exist for impossibly brief instants over impossibly tiny distances. But here's the question that matters most. Why should you care? If the weak force only acts across distances smaller than 1/1000th of a proton, if its carriers exist for less than 10 to the minus 25 seconds, if it's confined to the absolute tiniest scales of reality, does it really matter for the universe at large? The answer is yes. Profoundly, overwhelmingly yes. Because the weak force, despite its minuscule range, shapes the cosmos on the grandest scales imaginable. It powers every star in the sky. It drives the explosions that forge the heavy elements you are made of. It heats the interior of our planet. It determined the chemical composition of the entire universe in the first few minutes after the Big Bang. The weak interaction is the hidden engine behind some of the largest and most important processes in all of nature. And the best place to start seeing this is the nearest star, our Sun. The Sun is a ball of mostly hydrogen plasma, about 864,000 miles across. Its core temperature is about 15 million degrees Celsius. The pressure at the center is roughly 265 billion times the atmospheric pressure on Earth's surface. Under these extreme conditions, hydrogen nuclei, which are simply individual protons, are moving fast enough and are packed tightly enough that they can overcome their electromagnetic repulsion and get close enough for the strong nuclear force to take hold. This is nuclear fusion. Protons fusing together to build heavier nuclei, releasing enormous amounts of energy in the process. But here's what most people don't realize. The very first step of the process that powers the Sun is not a strong force process. It is not an electromagnetic process. The very first step, the reaction that initiates the entire chain of fusion events that makes the Sun shine, is a weak interaction. And without it, the Sun would not produce energy at all. The dominant energy-producing process in the Sun is called the proton-proton chain. It begins when two protons collide. Now, protons are both positively charged. They repel each other through electromagnetism. To get close enough for the strong force to bind them together, they need enormous kinetic energy, or they need to quantum tunnel through the electromagnetic barrier. This is already extremely unlikely. Most proton collisions in the Sun's core result in the protons simply bouncing off each other. But here's where it gets really improbable. Even when two protons do manage to get close enough for the strong force to act, they cannot simply stick together as two protons. A nucleus containing two protons and no neutrons, called helium-2, is violently unstable. It falls apart almost as soon as it forms. The strong force alone cannot hold two protons together without a neutron to help stabilize the system. So, for fusion to proceed, something else must happen in the same instant that the two protons come together. One of the protons must transform into a neutron, and this transformation, this identity change from proton to neutron, is a weak interaction. In that fleeting moment when the two protons are close enough for the strong force to act, the weak force must intervene. One proton must emit a W+ boson, converting one of its up quarks into a down quark, turning the proton into a neutron. The W+ boson then immediately decays into a positron and an electron neutrino. The result is a nucleus of deuterium, one proton and one neutron bound together, plus a positron and a neutrino that fly away carrying energy. This is the bottleneck of solar fusion. This single step where the weak force must convert a proton into a neutron during the brief instant that two protons are in contact, is fantastically improbable. The weak interaction is the slowest force in this context, not because it's intrinsically feeble, but because the conditions for it to act, having two protons within the weak force's minuscule range at the exact same time that a flavor change occurs, are extraordinarily rare. How rare? A typical proton in the core of the Sun will collide with other protons constantly. Billions of times per second, protons slam into each other. But the probability that any given collision will result in the weak interaction converting one proton into a neutron is staggeringly small. On average, a single proton in the Sun's core will exist for about 10 billion years before it successfully undergoes this reaction. 10 billion years. The Sun is only about 4.6 billion years old. So a typical proton in the Sun today has not yet undergone this fusion step. It's been bouncing around, colliding with other protons for billions of years, and it still hasn't fused. It might not fuse for billions of years more. Think about what this means. The Sun contains an enormous number of protons, roughly 10 to the 57 of them. Even though each individual proton has an incredibly low probability of fusing at any given moment, the sheer number of protons means that enough reactions happen every second to power the Sun. About 3.7 times 10 to the 38 proton-proton fusion reactions occur in the Sun's core every second. That sounds like an enormous number, and it is. But relative to the total number of protons available, it's a tiny fraction. The Sun is burning through its fuel extraordinarily slowly, converting only a minuscule percentage of its hydrogen into helium at any given moment. And this slowness is entirely because of the weak force. The weak interaction is the rate-limiting step. Everything else in the proton-proton chain happens relatively quickly once deuterium is formed.
Deuterium captures another proton through the strong force to make helium-3. Two helium-3 nuclei fuse to make helium-4, releasing two protons. These subsequent steps are governed by the strong force and electromagnetism, and they proceed millions or billions of times faster than the initial weak interaction step. The great physicist Arthur Eddington recognized in the early 20th century that the Sun must be powered by nuclear reactions. But it was Hans Bethe who worked out the detailed nuclear physics in the late 1930s, showing how the proton-proton chain and another process called the carbon-nitrogen-oxygen cycle could power stars. The critical role of the weak interaction in the very first step was central to his analysis. Now here is something profound to consider. This extreme improbability is not a flaw, it is a feature. It is the reason you exist. If the weak force were stronger, or if the W boson were lighter, or if the conditions for this transformation were less stringent, the first step of solar fusion would proceed much faster. Protons would convert into neutrons more readily. The Sun would burn through its hydrogen fuel far more rapidly. Instead of shining steadily for 10 billion years, a star like the Sun might exhaust its fuel in mere millions of years, or even less. Life on Earth took about 4 billion years to evolve from simple, single-celled organisms to the complex, intelligent beings hearing this today. If the Sun burned out in 100 million years, there would not have been enough time for complex life to develop. The weak force's improbability in this reaction is what gives the Sun its longevity. It's what makes stars slow, steady furnaces rather than brief, violent explosions. The weak interaction sets the pace of stellar burning, and that pace is precisely what allows planets to exist long enough for life to emerge, evolve, and eventually wonder about the forces that made it all possible. Every star you see in the night sky is powered by the same basic process. The details vary depending on the star's mass and composition. More massive stars burn hotter and can use additional fusion pathways like the carbon-nitrogen-oxygen cycle, which also involves weak interactions at key steps.
But in every case, the weak force plays a critical role, converting protons to neutrons or neutrons to protons at essential junctures in the chain of reactions that releases energy. Without the weak interaction, no star in the universe would shine the way stars actually shine. The sky would be dark. But the weak force doesn't just power living stars. It also plays a central role in how massive stars die. And the death of a massive star is one of the most violent and consequential events in the entire universe. When a star much more massive than the Sun, perhaps 8 or 10 or 20 times its mass, exhausts the hydrogen fuel in its core, it doesn't simply go quietly. It begins fusing heavier and heavier elements. Hydrogen fuses into helium. Helium fuses into carbon and oxygen. Carbon fuses into neon and magnesium. Neon fuses into oxygen and magnesium. Oxygen fuses into silicon and sulfur. And finally, silicon fuses into iron and nickel. Each stage burns faster than the one before. Hydrogen burning in a massive star takes millions of years. Helium burning takes hundreds of thousands of years. Carbon burning takes a few hundred years. Oxygen burning takes a year or two. Silicon burning, the final stage, takes roughly a single day. When the core fills with iron 56 and its neighbors on the periodic table, fusion stops. Iron is the end of the line for energy-producing fusion. Fusing elements lighter than iron releases energy. Fusing elements heavier than iron requires energy. When the core becomes iron, the star has no more fuel, no more energy source to support it against its own gravity. What happens next takes less than a second. The iron core collapses. Gravity crushes it inward at a significant fraction of the speed of light. In about a quarter of a second, a core that was roughly the size of Earth compresses down to a sphere about 12 miles across. The density becomes so extreme that protons and electrons are forced together, and here the weak force acts again. Protons absorb electrons and convert into neutrons, emitting electron neutrinos in the process. This is called neutronization or electron capture, and it is a weak interaction. The weak force is transforming protons into neutrons under the crushing pressure of gravitational collapse, creating the neutron-rich material that will become a neutron star. During this collapse, an almost incomprehensible number of neutrinos are produced. The weak force generates roughly 10 to the 58 neutrinos in a burst lasting only about 10 seconds. These neutrinos carry away about 99% of the total energy released by the collapse. That bears repeating. 99% of the energy of a supernova is carried away by neutrinos, particles that only interact through the weak force. The total energy released by a core collapse supernova is roughly 3 times 10 to the 46 joules. About 99% of that, roughly 3 times 10 to the 46 joules, goes into neutrinos. Only about 1% goes into the visible explosion, the expanding shockwave and light that we actually see. And even that 1% is so enormously energetic that a single supernova can briefly outshine an entire galaxy containing hundreds of billions of stars. The light alone is staggering, but the neutrino energy dwarfs it by a factor of 100. These neutrinos stream outward from the collapsing core in all directions. Most of them pass through the outer layers of the dying star without interacting at all, because neutrinos interact so feebly with matter. But the densities in the outer layers of a collapsing star are so extreme that even with the weak force's tiny interaction probability, a small fraction of the neutrinos do interact with the infalling material. They deposit energy into the outer layers, heating them, pushing them outward. This energy deposition is what actually drives the explosion. For decades, astrophysicists struggled to understand how supernovae explode. Early computer simulations showed that the shockwave produced by the core bounce when the collapsing core reaches nuclear density and bounces back outward, stalls. It runs out of energy before it can push through the outer layers of the star. The explosion should fail. The material should fall back onto the core. No supernova. The simulations were run again and again through the 1980s and 90s on increasingly powerful computers, and every time the result was the same. The shockwave launched by the core bounce would surge outward, ploughing through layers of silicon and oxygen and carbon. But the infalling material was immense, raining down at tens of thousands of kilometers per second. The shockwave also had to spend energy breaking apart iron nuclei in its path, and every iron nucleus it encountered drained energy from it. Within milliseconds, the shockwave would stall. It would grind to a halt a few hundred kilometers from the center, suspended between the outward push of the bounce and the inward crush of gravity. Then, the infalling material would begin to push it back inward. The explosion was failing. The solution came from recognizing that the shockwave doesn't have to succeed on its own. It has help. Behind the stalled shock, between the shock front and the newly formed neutron star at the center, there is a region physicists call the gain region. This is where the enormous flux of neutrinos streaming outward from the neutron star's surface deposits energy into the surrounding material. The neutrinos are pouring outward in unimaginable numbers, roughly 10 to the 58 of them in about 10 seconds. The vast majority pass straight through everything without interacting. But in the gain region, where densities are extreme and the neutrino flux is at its most intense, a tiny fraction of those neutrinos are absorbed by protons and neutrons in the surrounding material. Each absorption deposits a small amount of energy. But with so many neutrinos passing through, even a tiny interaction fraction adds up to an enormous energy injection. This neutrino heating, sustained over a period of perhaps 100 to several hundred milliseconds, gradually revives the stalled shockwave. The material behind the shock heats up. Convection develops, churning hot material upward toward the shock and cooler material downward toward the neutron star, where it can absorb more neutrino energy. Turbulence develops, adding pressure behind the shock. And eventually, the combined effect of neutrino heating, convection and turbulence pushes the shockwave past its stalling point and sends it ploughing outward through the rest of the star. The explosion succeeds. The star is torn apart. In 1987, a supernova was observed in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, about 168,000 light-years away. This was SN 1987A, the closest observed supernova in nearly 4 centuries. And about 3 hours before the visible light from the explosion reached Earth, neutrino detectors in Japan and the United States detected a burst of neutrinos. The Kamio-Kandei detector in Japan detected 11 neutrinos. A detector in Ohio detected 8. These tiny numbers, just 19 neutrinos total, out of the roughly 10 to the 58 that were emitted, confirmed the theoretical picture. The neutrinos arrived before the light because they were produced during the core collapse itself, before the shockwave had time to reach the surface of the star and produce visible light. The neutrinos streamed right through the outer layers, while the light had to wait for the explosion to break through. This detection was a triumph. It confirmed that core collapse supernovae produce enormous neutrino bursts, that the energy carried by neutrinos vastly exceeds the energy in light, and that the basic physics of the explosion is driven by the weak interaction. These 19 particles, each one a product of the weak force, each one having travelled 168,000 light-years across intergalactic space, provided direct evidence of the mechanism that destroys massive stars and creates the conditions for new solar systems to form. And supernovae don't just destroy, they create. The explosion scatters the elements forged during the star's lifetime: carbon, oxygen, silicon, iron, across space. But supernovae also create elements heavier than iron during the explosion itself, through processes that involve intense neutron bombardment. Many of the heavy elements on the periodic table, gold, silver, platinum, uranium, were forged in the extreme conditions of supernovae and neutron star mergers.
and the weak force is essential at multiple stages, governing the neutron-to-proton ratio in the material being processed, determining which isotopes are produced, shaping the chemical composition of the debris that eventually forms new stars and planets. The atoms in your body were forged inside stars that lived and died before the sun was born. The carbon in your cells was made inside a star. The oxygen you breathe was made inside a star. The iron in your blood was made in the core of a massive star during the final day of silicon burning before a supernova blew it into space. And at every stage, the weak force played its role, transforming particles, governing the pace of burning, driving the explosion that scattered these elements across the galaxy to eventually coalesce into the solar system, into the Earth, and into you. But the weak force shapes our planet in more direct ways too.
Deep inside the Earth, radioactive isotopes are decaying right now. Uranium-238, thorium-232, and potassium-40 are present throughout the Earth's mantle and crust, and they are undergoing radioactive decay. These decays are weak interactions. A neutron inside the nucleus of one of these atoms transforms into a proton by emitting a W- boson, which decays into an electron and an anti-neutrino. Energy is released, heating the surrounding rock. This is not a minor effect. Roughly half of the Earth's internal heat comes from radioactive decay. The total heat flowing from Earth's interior is about 47 terawatts, and approximately 20 to 25 terawatts of that comes from the decay of radioactive isotopes. This heat is what keeps the Earth's interior molten. It drives the convection currents in the mantle that move tectonic plates across the surface. It powers volcanoes. It drives the churning of liquid iron in the outer core that generates Earth's magnetic field. Without the weak force, these isotopes would not decay. Without their decay, the Earth's interior would have cooled long ago. Without internal heat, there would be no plate tectonics, no volcanism, no magnetic field. Without a magnetic field, the solar wind would strip away our atmosphere, just as it stripped away the atmosphere of Mars after Mars lost its magnetic field. Without an atmosphere, there would be no liquid water on the surface. Without liquid water and a stable atmosphere, life as we know it could not exist. The weak force, through radioactive decay, is literally keeping our planet alive. It maintains the internal heat that drives geology, protects our atmosphere, and sustains the conditions that make Earth habitable. Every earthquake, every volcanic eruption, every shift of a tectonic plate is powered in part by the weak interaction transforming neutrons into protons deep inside radioactive nuclei scattered throughout the rock beneath your feet. Radioactive decay, driven by the weak force, has also given scientists one of their most powerful tools: radiometric dating. By measuring the ratio of a radioactive parent isotope to its decay product in a rock or organic sample, scientists can determine how long ago the material formed. Carbon-14 dating, for instance, relies on the beta decay of carbon-14, a weak interaction in which a neutron inside the carbon-14 nucleus converts to a proton, transforming the atom into nitrogen-14. The rate of this decay is precisely known. Carbon-14 has a half-life of about 5,730 years. By measuring how much carbon-14 remains in an organic sample compared to how much was present when the organism died, scientists can determine the age of the sample with remarkable accuracy, reaching back roughly 50,000 years. For older materials, longer-lived isotopes are used. Uranium to lead dating can reach back billions of years, allowing scientists to determine the age of the oldest rocks on Earth, the age of meteorites, and ultimately, the age of the solar system itself. These measurements, all based on weak interaction decays, are how we know the Earth is about 4.54 billion years old. Every time a geologist quotes the age of a rock formation, every time an archaeologist dates an ancient artifact, they are relying on the weak force's ability to transform one type of particle into another at a precise, predictable rate. In medicine, the weak force has applications too. Radioactive isotopes that undergo beta decay are used in diagnostic imaging and treatment. PET scans, for instance, use positron-emitting isotopes. A patient is injected with a substance containing an isotope like fluorine-18, which undergoes beta plus decay. A proton inside the fluorine-18 nucleus converts to a neutron through the weak interaction, emitting a positron. That positron immediately encounters an electron in the surrounding tissue and annihilates, producing two gamma rays that travel in exactly opposite directions. Detectors surrounding the patient pick up these gamma ray pairs and use them to construct a detailed three-dimensional image of metabolic activity inside the body. This technique is invaluable for detecting cancers, evaluating heart conditions, and studying brain function. And every image it produces is made possible by the weak force, transforming a proton into a neutron inside a radioactive nucleus. Technetium-99m, the most widely used medical imaging isotope in the world, also relies on nuclear transitions involving the weak interaction. Tens of millions of medical imaging procedures worldwide every year depend on isotopes whose behavior is governed by the weak force. Now let's go back to the very beginning, the earliest moments of the universe. Because the weak force's influence on the cosmos doesn't start with stars, it starts with the Big Bang itself. In the first seconds after the Big Bang, the universe was unimaginably hot and dense. At temperatures above roughly 10 billion degrees, neutrinos and other particles were in thermal equilibrium, constantly interacting with protons and neutrons through the weak force. Neutrinos would strike protons and convert them into neutrons. Antineutrinos would strike neutrons and convert them into protons. These reactions ran in both directions, constantly, billions upon billions of times, keeping the number of protons and neutrons roughly in balance. But neutrons are slightly heavier than protons. At very high temperatures, this mass difference doesn't matter much. Both are produced in roughly equal numbers. But as the universe expanded and cooled, the balance shifted. Because neutrons are heavier, producing them requires slightly more energy. As the temperature dropped, the reactions producing neutrons became slightly less likely than the reactions producing protons. The ratio began to tilt in favor of protons. At about 1 second after the Big Bang, the temperature dropped to the point where neutrinos decoupled. The universe had expanded and cooled enough that neutrinos could no longer interact frequently with protons and neutrons. The weak interaction, which had been maintaining the equilibrium between protons and neutrons, essentially froze out. The reaction stopped. The neutron-to-proton ratio was locked in at roughly 1 neutron for every 6 protons. But neutrons are unstable. Free neutrons outside of atomic nuclei decay through beta decay, converting into protons with a half-life of about 10 minutes and 11 seconds. So during the minutes between neutrino decoupling and the onset of nuclear fusion, some of the neutrons decayed into protons, further reducing the neutron fraction. By the time nucleosynthesis began in earnest, about 3 minutes after the Big Bang, the ratio had shifted to roughly 1 neutron for every 7 protons. This ratio is critical. It determined how much helium the universe would produce during Big Bang nucleosynthesis. Almost all the neutrons that survived were quickly bound into helium-4 nuclei, because helium-4 is extremely stable. Each helium-4 nucleus contains 2 protons and 2 neutrons. With 1 neutron for every 7 protons, about 25% of the ordinary matter in the universe ended up as helium by mass, with most of the remaining 75% staying as hydrogen. Small traces of deuterium, helium-3, and lithium were also produced, but hydrogen and helium-4 dominated overwhelmed. This prediction, roughly 75% hydrogen and 25% helium by mass, matches observations of the oldest and most pristine gas clouds in the universe with extraordinary precision. It is one of the great triumphs of Big Bang cosmology, and it depends entirely on the weak interaction.
The weak force governed the conversion between protons and neutrons. The weak force determined when that conversion froze out. The weak force, through free neutron decay, continued shifting the ratio in the minutes before nucleosynthesis. The final chemical composition of the primordial universe was set by the weak interaction. If the weak force had been slightly different, if the W boson had been a little lighter, giving the weak interaction a slightly longer range, or if the weak coupling constant had been a little stronger, the neutron-to-proton ratio at freeze-out would have been different. More neutrons would have survived. More helium would have been produced. Less hydrogen would have remained for stars to burn later. The universe would have a different chemical composition, different kinds of stars. Possibly no stars at all if the balance shifted too far. If the weak force had been slightly weaker, fewer neutrons would have survived. Almost all matter would have remained as hydrogen. Stars would form, but their evolution would be different, because a star's helium content affects its structure, temperature, and lifetime. The universe we live in, with its particular mix of hydrogen and helium, with stars that burn at particular rates, with heavy elements forged in supernovae at particular abundances, all of this traces back to the weak interaction and the precise strength and properties it happens to have. The weak force is not some minor detail in the physics of the cosmos. It is one of the architects of the universe's chemical composition, its stellar populations, and its capacity to produce planets and life. From the first second after the Big Bang to the slow decay of isotopes deep inside the Earth billions of years later, the weak force is at work, transforming particles, setting the pace of stellar burning, driving the explosions that seed the cosmos with heavy elements, governing the primordial ratio of hydrogen to helium, heating our planet from within. Every one of these processes depends on the weak interaction's unique ability to change one type of particle into another. Every one of them operates through the exchange of W bosons, existing for fractions of an instant across distances smaller than 1,000th of a proton. And yet the consequences span the entire observable universe and the entire history of cosmic time. We've traveled deep into the machinery of the weak interaction. We've seen how it transforms one particle into another. We've watched it power stars, drive supernovae, heat our planet, and set the chemical composition of the entire universe. But now I want to step back and ask a different kind of question. Not what the weak force does, and not how it does it, but what it means. What does it mean for the universe that this force exists? What kind of universe would we have without it? And what does the weak interaction reveal about the deepest nature of reality? Let's begin with a thought experiment. Imagine a universe where the weak force simply doesn't exist. Everything else is the same. Gravity still pulls massive objects together. Electromagnetism still holds atoms together and carries light across space. The strong force still binds quarks into protons and neutrons, and binds protons and neutrons into nuclei. The only thing missing is the weak interaction. No W bosons, no Z bosons, no mechanism for changing the flavor of a particle. What happens? At first, nothing seems obviously wrong. Atoms still exist. Protons are stable. Neutrons, bound inside nuclei alongside protons, are stable too. The strong force holds them together. The electromagnetic force keeps electrons in orbit. Matter exists. So far, so good. But now try to build a star. A cloud of hydrogen gas collapses under gravity. The core heats up. Protons begin slamming into each other at enormous speeds. They get close enough for the strong force to act, but they cannot fuse. Not in the way they do in our universe. Because the very first step of the proton-proton chain requires one proton to transform into a neutron, and without the weak force, that transformation is impossible. A proton cannot become a neutron. It will remain a proton forever. Two protons cannot form a stable nucleus on their own. Without the weak force to convert one of them, the fusion chain never begins. The gas cloud keeps collapsing. It gets hotter and denser, but it never ignites. There is no nuclear fusion. There is no sustained energy source to support the gas against its own gravity. The cloud may collapse into something, perhaps a dense ball of hydrogen, perhaps something strange that doesn't exist in our universe, but it will not become a star. Not a star that shines, not a star that produces light and heat for billions of years, not a star that can warm a planet and sustain life. Without the weak force, there are no shining stars anywhere in the universe. The cosmos is dark. But the problems go much deeper than that. Without the weak force, free neutrons don't decay. In our universe, a neutron that isn't bound inside a nucleus will decay in about 10 minutes and 11 seconds, transforming into a proton, an electron, and an antineutrino through the weak interaction. But without the weak force, this decay cannot happen. Free neutrons are perfectly stable. They exist forever. This changes the early universe completely. In the first seconds after the Big Bang, the universe is filled with a hot, dense soup of particles. Protons and neutrons are being created and destroyed in equal numbers at extremely high temperatures. As the universe cools, in our universe, the weak force governs the balance between protons and neutrons, eventually freezing the ratio at about 1 neutron for every 7 protons. But without the weak force, this balancing mechanism doesn't exist. The ratio of neutrons to protons would be set by entirely different physics, likely closer to 1:1, since without the weak interaction, there is no mechanism to preferentially convert neutrons to protons as the universe cools. With roughly equal numbers of protons and neutrons, nearly all of the matter in the universe would be bound into helium-4 nuclei during Big Bang nucleosynthesis. Almost no hydrogen would remain. The universe would be composed almost entirely of helium, with traces of heavier elements, if any nucleosynthesis beyond helium could proceed. A universe of helium is profoundly different from ours. Hydrogen is the fuel that powers ordinary stars. Helium can fuse too, but only at much higher temperatures and through different processes. The chemistry of a helium-dominated universe would be radically different. Helium is a noble gas. It doesn't form chemical bonds under normal conditions. Without hydrogen, there is no water. Without water and the rich chemistry of hydrogen bonding, the molecular complexity that underlies life as we know it simply doesn't emerge. So a universe without the weak force is dark, cold, chemically sterile, and composed of matter that cannot transform. Particles are born with an identity they keep forever. Protons remain protons. Neutrons remain neutrons. Nothing decays. Nothing transforms. Nothing changes at the fundamental level. The universe is frozen in its initial configuration. Static. Dead. This reveals something profound about what the weak force truly is. It is not just another force among four. It is the force that makes matter mutable. It introduces the possibility of change at the most fundamental level of reality. Without it, the universe would be trapped in a single state, unable to evolve, unable to create the rich complexity that eventually gives rise to stars, planets, chemistry, and life. Every other force in nature is conservative in a deep sense. They rearrange particles. They move things around. They build structures and tear them down. But they always work with the same fundamental building blocks. The weak force is the only one that can change the building blocks themselves.
It is the engine of transmutation, the mechanism by which nature explores new possibilities. The reason the universe is a dynamic, evolving system rather than a static, eternal one. Now, I said earlier that the weak force follows strict rules when it changes particles. These transformations are not random. They are not chaotic. They obey precise conservation laws that dictate which changes are allowed and which are forbidden. Understanding these rules is essential to understanding why the universe changes in the specific ways it does, and not in other ways. You already know about conservation of energy and conservation of electric charge. These are universal. They apply to every force, every interaction, every process in the universe. The weak force obeys them too. When a down quark transforms into an up quark, the change in electric charge is exactly compensated by the charge of the emitted W boson. When the W boson decays, the charges of its decay products add up to exactly the charge of the original W boson. At every step, charge is conserved to absolute precision. But the weak force also obeys other conservation laws that are more specific. One of the most important is conservation of lepton number. Leptons are the family of particles that includes electrons, muons, taus, and their associated neutrinos. Each lepton is assigned a lepton number of +1. Each antilepton is assigned a lepton number of -1. Non-leptonic particles like quarks have a lepton number of 0. In every weak interaction, total lepton number is conserved. When a neutron decays, the lepton number starts at 0. Afterward, the electron contributes +1, and the antineutrino contributes -1, giving a total that is still 0. The books balance. This means the weak force cannot create an electron without also creating something that carries the opposite lepton number. This is why beta decay always produces both an electron and an antineutrino, never an electron alone. The conservation law demands it. Similarly, baryon number is conserved in weak interactions. Baryons are particles made of 3 quarks, like protons and neutrons. Each baryon has a baryon number of +1. Each antibaryon has a baryon number of -1. When a neutron decays into a proton, the baryon number stays at +1 throughout. The neutron was a baryon. The proton is a baryon. The total baryon count doesn't change. These conservation laws impose order on the weak force's transformations. They ensure that while particles can change identity, they cannot change arbitrarily. Nature does not permit a proton to spontaneously become an electron, because that would violate both baryon number and lepton number conservation. Nature does not permit a neutrino to become a quark, because that would violate lepton number and baryon number. The transformations that are allowed are precisely those that respect all the conservation laws simultaneously. This is important because it means the universe changes in structured, lawful ways. The weak force introduces mutability, but it introduces it within constraints. Particles don't just randomly become other particles. They transform along precisely defined pathways that conserve specific quantum numbers. The universe is changeable, but not anarchic. It is dynamic, but not chaotic. And this brings us to one of the most extraordinary discoveries in the history of physics, a discovery that may ultimately explain why the universe contains matter at all. This is the phenomenon of CP violation, and the weak force is the only known force that exhibits it. To understand CP violation, you need to understand 2 symmetries. The first is charge conjugation, denoted C. This is the operation of replacing every particle with its antiparticle. Every electron becomes a positron. Every quark becomes an antiquark. Every proton becomes an antiproton. The second is parity, denoted P, which we discussed earlier. This is the operation of reflecting everything in a mirror, swapping left and right. For most of physics, these symmetries hold. If you take any process governed by gravity, electromagnetism, or the strong force, replace all particles with their antiparticles, and mirror reflect the entire system, the resulting process obeys the same laws of physics. The laws of nature appear the same. CP symmetry is preserved, but the weak force violates CP symmetry. We already discussed how the weak force violates P alone, treating left-handed and right-handed particles differently. For a while, physicists thought that maybe the combination of C and P together was still conserved. Maybe if you both swapped particles for antiparticles and flipped left for right simultaneously, the weak force would look the same. That would be CP symmetry, and it would mean that even though the weak force distinguishes left from right, it treats a left-handed particle and a right-handed antiparticle identically. In 1964, James Cronin and Val Fitch conducted an experiment at Brookhaven National Laboratory that shattered this hope. They studied the decay of neutral K mesons, particles that can oscillate between their matter and antimatter forms through the weak interaction. Cronin and Fitch found that K mesons and anti-K mesons do not decay in exactly the same way. There is a tiny but measurable difference in the decay rates. The weak force treats matter and antimatter slightly differently, even when you account for the parity flip. CP symmetry is violated. The violation is small. In K meson decays, the asymmetry between matter and antimatter is only about 2 parts in 1,000. Later experiments with B mesons, heavier particles containing a bottom quark, found larger CP violation effects, up to several tens of % in certain decay channels. But in every case, the violation is exclusively a weak interaction phenomenon. No other force has ever been observed to violate CP symmetry. Why does this matter? Because of one of the deepest puzzles in cosmology, the matter-antimatter asymmetry of the universe. According to everything we know about particle physics, the Big Bang should have created exactly equal amounts of matter and antimatter. Every quark should have been paired with an antiquark, every electron with a positron, every particle with its antiparticle twin. And when the universe cooled enough for these particles and antiparticles to meet, they should have annihilated each other. Every particle finding its antiparticle partner, converting their combined mass into pure energy, into photons. The result should have been a universe of pure radiation. No matter, no antimatter, no atoms, no stars, no planets, no people, just light. But that's not what happened. Something produced a tiny excess of matter over antimatter. For every billion antiparticles, there were roughly 1,000,000,001 particles. When the annihilation was complete, the billion matched pairs had converted to photons. But that one extra particle in every billion had no antiparticle partner. It survived. And that tiny residue, that minuscule imbalance, is everything. Every atom in the universe, every star, every galaxy, every planet, every living thing, all of it comes from that tiny excess of matter that escaped annihilation. In 1967, the physicist Andrei Sakharov identified 3 conditions necessary for this matter-antimatter asymmetry to develop from an initially symmetric Big Bang. One of those conditions is CP violation. There must be some process in nature that treats matter and antimatter differently. Otherwise, any process that creates an excess of matter would be exactly balanced by a corresponding process that creates an excess of antimatter. The 2 excesses would cancel, and you'd end up with equal amounts of both, which annihilate to nothing. The weak force is the only known force that violates CP symmetry. It is the only known force that treats matter and antimatter differently. This makes the weak interaction the only known mechanism that could explain why matter survived. But there is a puzzle within the puzzle, and it's a deep one. Because when physicists try to work out the numbers,
try to calculate whether the CP violation we've actually measured in the weak interaction is enough to produce the universe of matter we see around us, the answer they get is troubling. And to understand why, you need to truly grasp what was at stake during those first moments after the Big Bang. Let me make sure you truly grasp what is at stake here, because this might be the most consequential fact in all of science. Right now, you are sitting in a universe made of matter, atoms, molecules, planets, stars, galaxies, you. All of it is matter. And in principle, none of it should exist. Think about what that 1 part in a billion really means. The annihilation that followed was the most thorough destruction event in the history of existence. Across the entire universe, in every region of space, matter and antimatter found each other and destroyed each other. Particles and antiparticles met and converted themselves into pure radiation, photons, light. The material universe was being erased, and it very nearly succeeded. If the annihilation had proceeded to completion, the universe today would contain nothing but a thin, cooling bath of light. No atoms, no stars, no structure of any kind. Just photons, redshifting into oblivion as the universe expands toward absolute zero. But that one extra particle in every billion had no partner. It had nothing to annihilate with. When the destruction was complete, when every matched pair had converted to radiation, that lone survivor remained. A remnant, a leftover. And that surviving residue, that 1 part in a billion that escaped the annihilation, is the entirety of the material universe. Every galaxy, every star, every planet, every ocean, every mountain, every cell in your body. You are not made from the matter that the Big Bang intended to create. You are made from the matter that accidentally survived the near-total annihilation that should have erased everything. The weak force, through CP violation, is the only known mechanism in nature that could have tipped the balance. It is the only force that treats matter and antimatter with even the slightest asymmetry. Every other force is perfectly blind to the distinction. Only the weak interaction has a preference, and that preference, amplified by conditions in the early universe that we are still working to understand, may be the sole reason that anything material exists at all. And here is what makes this even more astonishing. We know the weak force violates CP symmetry. We have measured it. We have confirmed it in multiple particle systems. But the amount of CP violation we have found so far is not enough. The asymmetry that the standard model produces through known weak interaction processes is many orders of magnitude too small to explain the matter we see around us. Something else must have contributed, some additional source of CP violation, perhaps involving particles or interactions we haven't discovered yet, must have amplified that tiny preference into the overwhelming material reality of the universe. We don't know what that source is. Finding it is one of the great unsolved problems in physics, and every experiment searching for it is probing the weak interaction. Because the weak force is the only place where nature has ever been caught treating matter and antimatter differently. Now, let me take you back to the earliest moments of cosmic history, earlier than the nucleosynthesis era we discussed before, back to a time when the universe was so hot and so dense that the weak force itself looked completely different from how it appears today.
Earlier, we explored how the electromagnetic force and the weak force are actually two manifestations of a single electro-weak interaction, separated by the Higgs field's influence. At everyday energies, they look completely different. Electromagnetism has infinite range and massless carriers. The weak force has minuscule range and massive carriers. But at very high energies, above roughly 100 giga-electron-volts, this distinction dissolves. The Higgs field's symmetry-breaking effects become irrelevant, and the two forces merge. In the universe, this unification was real. Before about 10 to the minus 12 seconds after the Big Bang, The temperature of the universe was above roughly 100 giga-electron volts, corresponding to about 10 to the 15 degrees Kelvin. At these temperatures, the Higgs field had not yet settled into its current state. It had not yet broken the electroweak symmetry. The W and Z bosons were massless. The weak force had infinite range, just like electromagnetism. There was no distinction between the two forces. There was only a single electroweak interaction, with 4 massless carriers, all behaving according to the same rules. During this electroweak epoch, all particles were furiously transforming into one another. The weak interaction, with its infinite range and massless carriers, was just as active and just as far-reaching as electromagnetism. Quarks were constantly changing flavor. Leptons were constantly converting between types. The universe was a seething cauldron of transformation, where nothing kept its identity for long. Then, roughly 10 to the minus 12 seconds after the Big Bang, the universe cooled below the electroweak transition temperature. The Higgs field underwent a phase transition, settling into the non-zero value it has today. This is called electroweak symmetry breaking. In an instant, the W and Z bosons acquired their enormous masses. The weak force's range collapsed from infinite to less than 1,000th of a proton's width. The single electroweak force split into the two apparently different forces we observe today. This phase transition is one of the most important events in the history of the universe. It shaped the fundamental forces as we know them. It gave particles their masses through the Higgs mechanism. It confined the weak force to its tiny range, locking away its transformative power inside the smallest distances. The universe went from a state of maximal transformation, where everything was constantly changing into everything else, to a state where change became rare, confined, and slow. The weak force didn't lose its power. It lost its reach. And that change in reach is what made the universe cold enough, stable enough, and structured enough for atoms and stars and planets and life to eventually form. There is one more aspect of the weak force that I want to touch on, because it reveals just how deep the connection between particle identity and the weak interaction goes. This is the phenomenon of neutrino oscillations. Neutrinos come in 3 flavors: electron neutrinos, muon neutrinos, and tau neutrinos. Each flavor is associated with its corresponding charged lepton. When a weak interaction produces an electron, the neutrino or antineutrino involved is always an electron type. When a weak interaction involves a muon, the neutrino is always a muon type. But in the late 1990s and early 2000s, experiments made a shocking discovery. Neutrinos can change flavor as they travel through space. An electron neutrino produced in the Sun can arrive at Earth as a muon neutrino or a tau neutrino. A muon neutrino produced in the atmosphere can arrive at a detector as a tau neutrino. Neutrinos oscillate between flavors, cycling through different identities as they travel. This discovery solved a long-standing puzzle called the solar neutrino problem.
For decades, detectors on Earth measured fewer electron neutrinos from the Sun than theoretical models predicted. Scientists checked the models, they checked the detectors. Everything seemed correct, but the numbers didn't match. The Sun appeared to be producing only about 1/3 of the expected electron neutrinos. The solution was neutrino oscillations. The Sun produces the correct number of electron neutrinos, but by the time they reach Earth, roughly 2/3 of them have oscillated into muon and tau neutrinos. The early detectors could only detect electron neutrinos, so they missed the ones that had changed flavor. When the Sudbury Neutrino Observatory in Canada, known as SNO, built a detector sensitive to all 3 neutrino flavors, it confirmed that the total number of neutrinos from the Sun matched predictions perfectly. They had simply changed identity during the journey. Takaaki Kajita at the Super Kamiokande detector in Japan and Arthur MacDonald at SNO
shared the Nobel Prize in 2015 for this discovery. Neutrino oscillations proved that neutrinos have mass, something the original Standard Model did not predict. Even today, we don't know the exact masses of the 3 neutrino types. We only know they're incredibly small, probably less than 1/10 of an electron volt, which would make them less than 1/5,000,000th the mass of an electron. But they're not zero. Neutrino oscillations represent the weak force's identity-changing power expressed in a different way. The neutrinos aren't exchanging W or Z bosons with anything as they travel. Instead, the quantum mechanical states that correspond to definite flavor, electron neutrino, muon neutrino, tau neutrino, are not the same as the states that correspond to definite mass. A neutrino produced as a definite flavor is actually a quantum superposition of different mass states. As these mass states travel at slightly different speeds due to their different masses, the superposition evolves. The neutrino's flavor identity shifts as it moves through space. It was born as one thing, it arrives as another. This is the weak force's fingerprint on the fabric of reality. The flavors that the weak interaction defines, the identities it creates and transforms, are not permanent labels stamped onto particles. They are quantum mechanical states that can mix and evolve. Identity itself, in the world of particle physics, is fluid. It is mutable. It shifts and changes according to the quantum rules that govern the weak interaction. So let me bring everything together. What is the weak force? It is not just the fourth force, some minor addition to a list that already contains gravity, electromagnetism, and the strong force. It is something qualitatively different. It is the force of transformation. It is the mechanism through which nature changes its building blocks, rewrites particle identities, and introduces mutability into a universe that would otherwise be frozen and static. Every other force acts on particles as they are. The weak force acts on what particles can become. It is the only force that can change a quark's flavor, turn a lepton into a neutrino, or convert a proton into a neutron. It operates at the smallest distances imaginable, through carriers that exist for the briefest instants conceivable, yet its consequences span the entire cosmos and the entire history of time. It powers the stars that light the universe. It drives the supernovae that forge the heavy elements. It governs the primordial chemistry that determined the composition of all matter. It heats our planet from within. It provides the asymmetry between matter and antimatter that may explain why matter exists at all. It connects different generations of particles through neutrino oscillations, revealing that identity in the quantum world is fluid rather than fixed. Without the weak force, the universe would be a dark, static, frozen place. Matter would exist, but it would be inert. Particles would have permanent identities they could never shed. Stars would never shine. Elements heavier than hydrogen and helium would never be created. The rich chemistry that underlies life would be impossible. Change itself at the most fundamental level would be forbidden. But the weak force does exist, and because it does, matter is not static. Particles are not permanent. Identity is not fixed. The universe is a dynamic, evolving, transforming system where one type of matter can become another, where stars can burn for billions of years, where dying stars can seed space with the atoms of future worlds, where atoms can decay and release energy, where the very building blocks of nature can shift and change according to precise quantum rules. This is what the weak interaction truly is. It is the reason matter is unstable, transformable, and alive with possibility. Not alive in the biological sense, but alive in the physical sense. Matter in our universe has the capacity for change built into its foundations. That capacity comes from the weak force, and from the weak force alone. The next time someone tells you the weak force is weak, remember what you've learned. It isn't weak, it's hidden. Its immense power is confined to the tiniest distances by the Higgs field's influence on its carriers. But within that tiny range, it does something no other force can match. It changes the very nature of matter. It rewrites the identity of particles. It makes the universe a place where things can become other things, where the present is not a permanent prison, where transformation is woven into the deepest fabric of reality. The universe is not a still photograph. It is a story, and the weak force is what allows that story to have chapters, turning points, and new beginnings. It is the force that gives matter the freedom to change, and that freedom, exercised trillions of times every second in every star and every atom and every neutrino streaming silently through the cosmos, is what makes the universe the rich, complex, beautiful, living thing that it is.